The last thing we're going to do today is we're going to talk about some usage considerations to keep in mind when you are contemplating applying Java ConditionObject. So the first thing to note, Java ConditionObject is a highly flexible synchronization mechanism. It allows threads to cooperatively suspend and resume their execution based on shared mutable state. For example, you can take turns sharing a critical section, as we've seen with examples of putting things in and out of the queue, taking things from the array blocking queue. So you can have one thread kind of parked off to the side while another thread does its thing. Then the other thread could park itself, and the first thread comes back in, and so on and so forth. Lots of different use cases can be applied here. A user can define multiple condition objects. You can have condition object 1, condition object 2, just like we did with not empty and not full conditions for the array blocking queue. And each condition object can provide a separate wait set. You have different sets that work in different ways. You have to be careful using condition objects, however, to avoid certain types of concurrency hazards. As we've talked about several times now, you should almost always use them in a loop. And there's a couple of reasons for that. The main reason is that you need to deal with the inherent non-determinism of concurrency, and therefore you have to retest or test state that's being waited for because it could have changed in the intervening time between when signal is called and when await returns with the lock held. So that's subtle. There's lots of windows for race conditions and other problems to occur. And one of the other problems which necessitates the use of a loop is to guard against spurious wake-ups. And I will let you read the Wikipedia article about spurious wake-ups. It's a very esoteric thing, and it has to do with the implementation of condition objects on some multiprocessor or multi-core processors. And it's rather esoteric, but the long and the short of it is it's possible for situations to occur where a thread might return from await without being signaled explicitly. And really, when all is said and done, it's not that much different from a case where you were signaled explicitly, but by the time you return from await, the condition's already changed. So in any case, using this loop will cause these problems to go away. They'll solve those problems. You always use condition objects in conjunction with a lock, typically a reentrant lock, and that is needed to avoid something called the lost wake-up problem. I'll let you read about that. Lost wake-up problem is a thread calls signal or signal all. Another thread is between the test of the condition and the call to await, and therefore, by the time it gets to where it needs to be, no threads are waiting, even though signal or signal all was called, and that's because the lock wasn't held properly. So we want to avoid the lost wake-up problem, which is described down here in this link. Await internally releases and reacquires the associated lock. You do not have to do that. It does it for you. It's very nice on your behalf. And then another point to keep in mind, and this is particularly important, and one of the reasons why we have condition objects as opposed to built-in monitor objects alone, is that choosing between using signal versus signal all can be subtle. Whenever possible, use signal, since it's more efficient, and it's more efficient because it avoids the thundering herd problem, where all the threads are awakened, stuck onto the queue of the reentrant lock that's associated with the condition object, and then they all compete for that lock, and it's inefficient. So these are the conditions under which you should use signal or signal all. The conditions under which signal can be used is if you have uniform waiters and one in, one out semantics. And we're going to use the array blocking queue as an example to make this more concrete. So uniform waiters says you can use signal if you're waiting only for one specific condition. For example, we're waiting to see if the queue is not empty. So that's one kind of condition. If you only wait, if all the waiters that are waiting on the condition are waiting for the same thing, then you can use signal. And you want one in, one out behavior, which is a signal on the condition object enables at most one thread to proceed. And that's exactly what we want with our array blocking queue. We want to say, hey, whoever is waiting, however many threads are waiting, let one of them go ahead. Because I just put something back in the, I just inserted something into the queue. So somebody can wake up and go for it. The array blocking queue in Java satisfies both of these conditions. So it can use signal instead of signal all. Another thing to keep in mind, ConditionObject inherits the wait, notify, and notify all methods from Java object. Do not mix and match these methods. I will say this now. I will say it again when we do assignment 2B. People will forget. They'll get it wrong. So just be very careful. Don't forget which methods to use under the right circumstances. And you should also name ConditionObject fields to reflect their usage. So they typically use not, like not empty, not full, because you're waiting for something to be not something. I'm waiting for something to be not empty. I'm waiting for something to be not full. You'll find ConditionObject appears in a lot of places in the Java locking packages themselves, but not much else. So they're typically hidden behind other higher level abstractions like array blocking queue or linked blocking queue. Okay, so that is the end of our usage considerations discussion for Java ConditionObject.